Thanks, Alex. Thanks, everyone, for being here. And thanks to Alex, Josh, Olivia, Dan, for organizing such a nice workshop. So I want to present you about evolutionary dynamics of strategic classification. And this is actually work also led by Marta. So as Christine yesterday, I hope I don't disappoint Marta. And it's also a collaboration with Flavia Barsotti at ING, which is the largest bank in the Netherlands. So this is actually a fun project that involved the collaboration between academia and a bank. And I promise there will be evolutionary game theory involved. So I'm not going to show you a super sophisticated method or a new theory, but what I'm going to try to convince you is that evolutionary game theory can find really cool applications in data science, and particularly even with banking applications. So if you wish, an alternative title should be, why should bankers and data scientists care about mathematical biology? And you saw that there was classification in the title. So I'm going to use this term classification algorithms. So classification algorithms are algorithms used nowadays to classify people in several domains. For instance, if you apply to a loan or to credit in a bank, then a classification algorithm takes your characteristics, your features, and then it will output yes or no. Should this person have a loan or not? Is this person high risk or low risk? Now, a key assumption about these algorithms is that they are trained in a distribution of data that is similar to the data where they are going to be tested or implemented or used in reality. However, people can act strategically. Nowadays, these algorithms, they should be transparent. There's actually a very strong push for these algorithms to be understandable for people and to provide information about why someone was classified in a certain way. And this also means that over time, people can use this information to adjust their own features. So you can also start to see that if people are adapting over time, then algorithms also need to be retrained, which means that they will function in a different way. People will adapt differently. So we have two populations, one of users, of people, another of algorithms that are co-evolving with each other. And what we've been trying to do is to apply evolutionary game theory as a tool, as a mathematical rigorous tool to understand this co-evolutionary process. Okay? So first of all, what do I mean here by strategic adaptation? So let me give you a super simple example that I think you will recognize very easily. So nowadays, there are several health insurance companies, for instance, that offer benefits if people are healthy. For instance, you can submit the number of steps that you take in a day, measured through a wristband, through a Fitbit, for instance, and then based on these, you can receive rewards. This company here is paying $1 a day if you take at least 8,000 steps. So this is a very rudimentary, super simple classification algorithm, right? So here your feature is the number of steps. And if this number of steps goes above a certain threshold, then you receive a reward. You are classified as fit. Of course, this can be a win-win situation, right? People can become healthier over time, and insurance companies might have less costs with someone. However, people can act strategically, and there are several ways in which the number of steps that you submit are not the actual steps that you take. So you can add your Fitbit to a puppy, you can use a drill, you can swing your arm following a specific pattern. So all of these are ways in which you can try to game this system, this algorithm. Okay, so let's start to think in terms of a model. So what do we have here? So to a fundamental level, we have people are here being classified according to two different features. So we have, on the one hand, the real feature here on the horizontal axis, which is the actual number of steps that someone takes. And notice this is costly to change, right? So if you want to take more steps in a day, then you have to take some effort. You have to run. You have to go outside. And on the vertical axis, we have the observable feature. So how many steps you submit to this company, to this institution. And this is much cheaper to change. Now, those circles there represent people. One key aspect to note here is that your success, so your actual quality of being healthy or not depends on the real feature. So it depends on the horizontal axis. But the institution is making a decision based on the vertical axis, on the observable feature. And now you can adapt following different ways. You can game or fake if you wish. So this means that you just go up without increasing your real feature. You just change your observable feature. Or you can move along the diagonal. In that case, you are actually improving your condition. You are running, you are taking steps outside. Now, of course, this is a super simple toy example, but this problem is quite prevalent. There are reports of how people submit false information when applying to loans, for instance. This is last year FICO survey saying that 1/3 of Americans say that lying is actually acceptable when applying to a loan. In Australia, 1/5 of people have admitted not to tell the whole truth when applying to a loan. And this involves different strategies, for instance, understating living costs or understating existing debts or overstating income. And there's other domains. Of course, banking is the one that we have been using as a key example. But in college admissions, inflating extracurricular activities, or nowadays, super recent example, using ChatGPT to produce an essay. Recruitment tools, adapting strategically information on your CV, hate speech or spam detection. So if you know how the algorithm works, you can adapt the keywords that you use strategically, or even social welfare programs. Talking about the last one, I think this is also a very interesting example. So this is an example published at American Economic Journal, 2011, about manipulation of social welfare eligibility in Colombia. And I think even visually is quite striking. So this is how a population distributes according to a poverty index score. So for this program, people receive benefits if their poverty index score is below a certain threshold. And the threshold is given by that vertical line over there. So you see that this follows a nice distribution. And then what happened is that in 1997, the government in Colombia disclosed the algorithm. So they made the algorithm transparent so that people could fully understand how the different features, like income that they have, debt, number of kids, and so on, how that is all aggregated to form the index. And then you see that afterwards, you started to have this very particular distribution where you have this discontinuity exactly at the threshold. So somehow people started to change their features in such a way that they are exactly below the score to receive these benefits. Okay, so so what we have here, once again, is this idea that people are adapting to a decision rule or to an algorithm, and this suggests that the algorithm should be retrained. And if you think about this as a long-term process, then we have algorithms and people co-adapting to each other, and evolutionary game theory is a wonderful tool to understand some aspects of these co-evolving dynamics. So this is what the key research question here is, what co-evolving dynamics will result if we have this process? Okay, so let's start thinking about a super simple stylized model to shed some light on this process. So let's assume that we have three populations. One population of institutions, and institutions here can be strict or lenient, so you can have a higher decision threshold or a lower decision threshold. We have a population of good users, so these are the users that are in good standing, that they deserve a certain service or that they are likely to repay a loan. And we have a population of, let's say, bad users that are not in good standing, so they are not likely to repay a loan. And the strategies of the good user, we assume to be just do nothing or adapt, still improve. And for the bad users, they can decide to actually improve, honestly, somehow their features, or to submit false information, or to somehow try to game the system. And now we can also get back to our two-dimensional space and see how this intuitively plays out here. So you see that institutions can apply different levels, different thresholds on the observable feature that users have, and then users can improve, so moving along the diagonal, or fake, just moving along the observable feature, and the good users can either do nothing, stay on the same location, or improve. And now to each of these outcomes, there's actually an equivalent, there's actually a result, an outcome, if we think in terms of a confusion matrix. So in data science, in classification algorithms, people discuss a lot these confusion matrices, which in a way convey how confused the algorithm is about a certain outcome. So we can have true positives, which are people that deserve to be classified as positive and are actually classified as positive. So here on top, we see that that individual there is above the threshold of the company, but also above the threshold that determines his or her success. We have a true negative in the bottom. So someone that doesn't deserve to be classified as positive and is in fact classified as negative. And then we have a false positive there in red, which is someone that should not be classified as positive, but actually the observable feature tells that no, these individuals should be classified as positive. And what it means for now the company to move the decision threshold, it means that we are changing these outcomes, right? So now if the company becomes stricter, there is an individual that now is classified as a true negative. So we are able to classify correctly that negative example, but we are also becoming stricter with people that would deserve to be classified as positive. Okay, so now let's take one step closer to a payoff matrix. So what we can do is we can identify for each combination of strategies of our institution and users, we can identify one entry of a confusion matrix. Let me take some time here. So if an institution is lenient, so if an institution is having a medium threshold and the good user is not adapting, that's fine because it's a good user. It deserves to be classified as positive. So this is a true positive. If the good user adapts, still fine. This will result in effort that is not needed, but still the individual is classified as positive. Now, if an individual is in bad standing and is faking, now this individual will be classified as a false positive. This is the concerning bit for institutions. But if the individual honestly improves, then the individual is classified as a true positive. And for the other row, we can have a similar reason. Okay, so now let's actually take the step from a confusion matrix to a payoff matrix. Now what we can do is we can move from this space of outcomes of a classification algorithm to a space of payoffs. And as an example, so the entries that we have here are we draw the benefit for a company to classify someone as a true positive. Right? So for a bank, there's of course benefits of conceding a loan that is going to be repaid. And we have here with lambda the loss for an institution of having a false positive. So offering a loan that is not going to be repaid. And these last three payoff entries are parameters, are the outcomes for the users. So B is the benefit of being classified as positive, of being accepted to college, of being accepted for a loan, and so on. CF is the cost of faking. So the cost of tying your wristband to the puppy, for instance. So you can see that this has a small cost. And CI is the cost of improving, cost of actually taking the steps and doing sports. And this is the restriction that we consider. So the costs are always lower than the benefit. So it's always better for someone to do something to be classified as positive. So being classified as positive is highly desirable. And the cost of improvement is higher than the cost of fake. So what we have here ultimately is a tree population to strategy game that from now, basically, I could skip this part. So this will be supernatural for everyone here. So now we can apply the tools that we are used to of stability analysis, of learning the trajectories, and so on. But because I have some minutes, I will continue anyway. So we can define a replicator equation. As we have already learned since Arne's talk yesterday, that I'm pretty sure you're familiar with. And we can have a replicator, and it's a three-dimensional system. So we have a replicator equation for the institutions, for the good users, and for the bad users. The only thing I want to highlight here is that we are considering this evolutionary rate, which of course usually it has a certain biological meaning. Here, it can also have an important meaning for data science. So this can represent how often, how frequently we are retraining our algorithm, given how fast people adapt. So it's a relative, the relative frequency of retraining compared with users' adaptation. Also, to make things clear, we are living in this cube, right? So we have three populations. For each population, we have two strategies. So all the possible states of our population lie within this cube, where in the vertices we have the monomorphic states, where inside each population everyone is using the same strategy. Okay, so now let's see some results, and let's first focus on the imperfect classifier. So this is a classifier that cannot tell whether individuals are faking. So if a bad individual is faking, then this will result in a false positive. So if this is the case, then what happens is that for the parameters that we consider of interest, there's only one state that is always stable, a state where companies do high, so they are quite strict. Bad users adapt, so good users adapt, and bad users fake. So we always end up in these contexts there. And this is not ideal. And it's not ideal because we have a very high social cost. So here, social cost is defined by the fraction of good users that need to adapt, that need to do an extra effort to actually be classified as positive. Also, from the company perspective, things are not so great. So the algorithm is highly accurate. So we have a very high number of true positives and true negatives, but ideally we want these true positives to be as high as possible. So we want to offer loans that are repaid to everyone. Now, what's nice here is that this captures quite well what people have been discussing for a long time in machine learning about this problem of strategic classification. And the known kind of the baseline for most models is this idea that if we have an imperfect classifier, and if algorithms need to be trained with constraints such that we reduce these false positives, then we are going to increase social cost. Okay? So this is the known fact in machine learning. And this is reassuring. It means that, okay, we are applying a super simple evolutionary game theoretical tool, but even so, we can capture what people have been discussing in the machine learning literature. And now from here, from these, let's say, sanity check, we can start to play with things that people are also discussing in machine learning. For instance, what happens if we offer algorithmic recourse? So algorithmic recourse is the idea that we should allow individuals to improve themselves. We should provide explanations. We should provide the means for individuals that are now classified as negative to improve themselves and to, in the future, be classified as positive. So if we do this now, what we assume here is that the bad individuals that improve, also for the strict classifier, they should be classified as positive. They should be given a chance. And if we do this now, we have all the beauty and might of frequency dependency and evolutionary game theory. So what we see is that, first of all, now we don't have a unique equilibrium. We actually have multiple stable equilibria. And in some regions, depending on initial conditions, we can even incur in these cycling dynamics where bad users and institutions are, in a way, well, cycling over time. This is good because social cost is now much lower. Still, it's not ideal because for companies, there's these bursts of false positives. So what happens now is that after a critical threshold of lenient institutions, when institutions become lenient, then individuals start to become bad over time. If they become bad, then institutions are becoming stricter. But if institutions become stricter now, bad users have an incentive to actually improve, which is good. And it's something that didn't exist before. As they improve more and more, institutions will now have an incentive to become lenient again, and so on. And we have these cycling dynamics. Also, something that I think that's pretty cool is the fact that by changing this relative evolutionary rate, we are affecting the size of the basin of attraction to the equilibrium that we want, in a direction that the conclusion here is that if we retrain more frequently the algorithms, that actually will end up in a state that's desirable, where companies are not strict and where good individuals don't have to improve more often. So there's also an analogy between relative evolutionary rates and speed of retraining. Okay, and last set of results that I want to tell you about. All the previous results were with infinite populations, applying the replicator dynamics, but we can do a similar type of analysis using a finite population. Of course, in reality, there's many more users than institutions. Right? So what we are playing now with is a scenario where we just have a few institutions, but we have a very large population of users. And in this square, what you see here is a summary of our fixation probabilities. So if you see a direction, if you see an arrow there, it means that a mutant of a certain strategy can invade and fixate in the resident population with a probability higher than neutral. And this here means that these two strategies are actually neutral. So the fixation probability is 1 over the population size. Now, I will just summarize the most interesting conclusion that we found here. And it is that for this case, if we have these asymmetric population sizes, then even if we have a manipulation-proof classifier, we can have a quite high prevalence in a setting that it's not socially desirable. So if we have a very small population of institutions, then we end up spending a considerable amount of time in a state where companies are super strict and good individuals need to adjust. And here, these are just, we are doing the small mutation approximations. We are just treating these, using these fixation probabilities to define a Markov chain and then computing the stationary distribution over these monomorphic states. And this was quite surprising, the fact that surprising at the same time intuitive. So it means that if the population of institutions is small, then in a way the dynamics on the institution population is more noisy, and so we end up staying more often in the suboptimal state. Okay, and to conclude, some conclusions. So what I wanted to show was an example where evolutionary game theory can actually be pretty useful to understand this co-evolving dynamics between classification algorithms and users. We've been applying these models in collaboration with people in banking to understand these co-evolving dynamics. So we are building different scenarios and then try to anticipate what is going to happen. First of all, we recovered well-known results in strategic classification that people have been discussing in machine learning. And from here, we are also able to provide new perspectives and insight. First of all, that if you provide algorithmic recourse, then you are likely to have these cycling dynamics that you should account for. And in particular, you should invest more in retraining often your algorithms. And second, we observe that relative population sizes of institutions in users can actually also play a role. So if you have a smaller population size for institutions, then we might have high social costs, even if we have a manipulation-proof classifier. And just as a very final remark, from this experience, what we've been finding is that actually in this domain, evolutionary game theory is a pretty nice communication tool as well. So when we have to discuss these payoff matrices and these trajectories with people in a completely different field in a bank, actually evolutionary game theory provides a nice common language that people can understand, especially this idea, even if people do not understand evolutionary stability, they understand quite well trajectories in a strategy space. And then even with a super simple model, we can provide some practical insight, which is cool. And what we are trying to do now is how to use this insight to generate synthetic data that people can train their algorithms on. So this idea of thinking in long term in machine learning is not for advanced machine learning. And what we can offer here is a way of reasoning about timescales, about evolutionary rates, and this can be quite useful for this step here of generating synthetic data. So there are 2 papers summarizing these results. One of them we are going to present in a computer science conference next week. So it's not online yet, but I'm very happy to share. Yeah, and if you are around Amsterdam, feel free to visit us in our group. It's not the most sunny city ever, but we have a new building, so it's actually quite cozy inside. So don't feel dissuaded to visit us just because of the weather. Thanks a lot, everyone.